Okay, hello, good day to everybody. Today we're going to check concepts about electric charge and electric field. We will be using Serway and Hewitt's Physics for Scientists and Engineers, 10th edition, chapters 22 and 23. In this first presentation, I will only cover chapter 22. This is how the book looks like, and the presentation will be only about the first four points here. On the second video, I will cover Gauss law. So let's get started with the concepts, the basic concepts here for electricity. And the first one is electric charge. Electric interactions are obviously those that are not gravitational interactions. So we look at, for example, the kitty cat here. She's got some styrofoam chips stuck to her body. So we can very easily conclude that this is an electric interaction. We've seen that electric charges are divided into positive and negative charges. So this is what we call the polarity. And we know that the force between electric charges are proportional to the magnitudes of the charges, and they obey an inverse square law, which means that they are proportional to the inverse of the square of the separation between them. We also find that charges are quantized, so the minimum possible charge available is 1.60 times 10 to the negative 19 coulombs. These are the units for electric charge. And we know that charges of different sign attract each other, and alike charges will repel each other. So let's see how do we quantify this? How do we write down equations? And to do this, we will study Coulomb's law. So before writing Coulomb's law, let's check two possible materials that we will find throughout this investigations, these studies. We find conductors and insulators. Conductors are those for which charges are relatively free to travel along the material. In the case of metals, they will be traveling mostly in the surface, and not all the time, but most of the time. In plasmas, which are ionized gases, so this is a gas where the molecules have either lost or gained electrons. And also we have to look at liquids containing ions dissolved in them. For example, sodium and potassium, chlorine are mostly the probably the most usual of these ions. Now, those are conductors. The case of insulators are probably, we could say, that the opposite. In this case, electric charges are not readily transporting charge. This means that the ions are stuck on a particular position, and the electrons are also stuck at a particular position. Now, to calculate the magnitude of the forces between electric charges, we will refer to Coulomb's law. Down here we have the force, as we mentioned earlier, is proportional to the magnitude of the charges and inversely proportional to the square of the distance between the charges. Remember that the charges could be either point charges or could be distributed over certain materials, and the letter K represents Coulomb's constant, which is 8.99 times 10 to the ninth power of Newton square meter over square coulomb. These are the units, and if you substitute them in the equations, you'll see that once we work out the units, we will stay with newtons for forces, which is obviously the natural units, international system units for force. Now, remember that forces are vectors, and as such we ought to calculate magnitude and direction. So usually a force, remember that this is a three-component vector, and we usually symbolize it or represent it as three numbers, one next to each other, or we can also represent these forces as the magnitude times a unit vector which points in the direction of the net force. Remember that whenever we have several forces, we have to sum them to add them in each direction. So for example, if we wish to calculate the force on this charge up here, we would have to calculate the force between this charge and each one of the other two forces. In this case, forces are repulsive, so we will have one force pointing in this direction, the other force pointing, let me use another color, pointing in this other direction, and we would have to break down these forces into x component and y component before we add them together. After we've done that, we use Pythagoras theorem to calculate the net force, right? In 3 dimensions is pretty much the same. If we wish to calculate the force acting on this charge at point A, we should calculate all the forces due to each one of these 1, 2, 3, 4, 5, 6, and 7 charges on the corners of the cube there. So it's pretty intensive. However, it is straightforward, and never forget that you have to um, make use of the symmetry of the system, and probably we can work less. For example, charges 1 and 5 are at the same distance to Q. Also charge number 6, they are all at the same distance. Charges 2, 7, and 4 are at the same distance to Q at point 8, and the remaining one is a little bit farther, but we can use these shortcuts in order to reduce the number of calculations that we should do. But never forget to break down the forces into x, y, and z, do the calculations, and then use Pythagoras theorem to calculate the magnitude of the force. Now, let's go to another probably new concept for you. This is the concept of electric field. What is an electric field? Well, when there are two forces interacting with each other, we have a force between them, but if we take away one of them, we will remain with the electric field of the other charge. So for example, in this picture over here, if I have charge Q0, then there will be a force acting on this Q0, but if I take it away, what I will remain having at this point would be only the field. Therefore, the formula here, electric field equals force divided by charge Q0. Remember that this charge Q0 is the one that I took away from the picture, and I stayed with the electric field due to charge Q. Now, usually this model charge that I take away is taken as if it were a positive charge, so that the electric field of a positive charge points away from it. It is a vector that points away from it. A charge with a negative sign has an electric field pointing into the charge. So these arrows here represent the electric field. Of course, the electric field is not limited to those points. I can calculate the electric field at any point in space. And if I wanted to calculate at any other point, well, I would have to figure out the direction. So electric field is a vector, and as such, if I had more than one charge, I would have to add the electric fields due to each one of the charges. So for example, in this case, the positive charge will contribute electric field in this direction, while the negative charge will contribute with an electric field in the direction of the blue arrow. Remember, the positive charges have fields pointing away from them, and negative charges have fields pointing towards them. So the vector addition of these two charges will be the arrow that is represented here. At the point that I selected is to the right, but at any other point I would have to perform the vector addition that I talked about before, just the same way as I did with forces. So to calculate the electric field, I will use a formula very similar to Coulomb's law, which is right here. So we have a Coulomb's constant, the charge which is responsible of generating the field, and the square of the distance from the charge to the point where I want to calculate the field. In this case, it would be from the point the charge is at to the point where the electric field is being calculated. So usually we represent electric fields by electric field lines, and here I added a couple of examples. Electric field for two charges of equal magnitude but different sign. Then down here, two charges of the same sign and the same magnitude. It is important to check that at point C there is zero electric field. If you do the vector addition of the fields, you will find that at C we have zero field. And for two charges with different magnitudes, well, the electric field lines turn a little different from the former case where the magnitudes were equal, but we can always write a program, for example, to try to figure out these lines, and of course we can do it experimentally as well. Now, in the case that I just discussed, we have point charges, individual charges isolated at a certain position. However, electric charge could be distributed over over a rod or a surface. In this case, if I distribute the charge over a linear domain like this is a rod, then I will have a linear distribution. And in the case, well, the same thing over here. And if the charge is distributed over a surface, then I will have a surface distribution. Let me make a pause at this point. All right, sorry for the pause. I'm back. I noticed that the formulas for linear distribution and surface distribution were wrong, and in this image they are already corrected. If you rewind a little bit the video, you'll see that they were wrong before. Now, linear distribution of charge means that there is a charge Q distributed over a length L. So in this case, there are charges distributed over this rod. And for the surface distribution of charge, there is a total charge Q distributed over a surface. So all this surface has charge distributed on it. So in this case, if I wanted to calculate the field E at a certain point, I would have to calculate the field generated by a small distribution, a small part of the charge. So in the linear case, I will divide the domain into little pieces dx, and I will see that each one of these pieces dx has a small amount of charge. So dq over dx, so that the charge at this small portion of the rod is exactly equal to dq, and this equals lambda dx. Now, once I do the calculation of the differential field contributed by this small amount of charge at point P, I will sum all the distributions starting at this point, ending at this point, to get the total or net electric field caused at point P by the whole charge distribution. If I do that, I end up with this equation, this formula here, If I want to calculate field at point P, I can use this equation over here. A is the distance from P to the initial point of the rod, and A plus L would be the distance to the end point of the rod. Now, if the charge were distributed on a ring like this, the dq, or differential part of the charge, is also taken as a little piece of the ring, and we add all the contributions from the ring by doing an integral just as we did before. And we once we do that integral, we obtain this formula where the electric field that we are calculating is done at P, distance x is a distance from the center of the ring in the direction of the axis of symmetry of the ring, and A is the radius of the ring. Now, if we take advantage of this formula and now suppose that the charge is the dq is over a small ring in a disk, we can do a smart integral. We can state this integral in a smart way, and after calculating the integral, we will end up with an expression like this, where well, k here is again the Coulomb's constant. Sigma here is the distribution, the surface distribution of charge, so net charge divided by A, and r is the radius of the disk, x is the distance from the center of the disk to point P, and remember that this is done along the symmetry axis of the disk. So if you want to write down, record these three formulas, we will use them later on. And just to make sure that you have a formula for everything, every possible, well, not every possible distribution, but important charge distributions. So I added this formula sheet for which you can find the charge distribution, in this case a single point charge, and the corresponding formula to calculate the field. This is a charge Q distributed over a conducting sphere. So all the charge is on the surface of the sphere. Here we have for the outside of the sphere, for the inside of the sphere, different fields. For an infinite wire, infinite conducting cylinder, solid insulating sphere, and so forth and so on. Very important to check the field for a sheet of charge. A sheet, remember, like a sheet of paper, plane. We consider it as an infinite plane, and we will be using this electric field very commonly. Well, we will use it a lot. Now, once we know what the electric field is for different distribution, let's see what happens to a charge whenever it enters a certain electric field. In this case, we have a uniform electric field. Uniform means that it is constant through time and through space. So in this case, if we place two sheets with a negative charge up here and positive charge down here, we will have that inside, in between those two sheets, two planes, we have the same magnitude of the electric field at all points between them. So this is what we call a uniform electric field. So what happens to a point charge when it enters this field? Well, a charge Q will experience a force F, and according to Newton's second law, that force equals mass of the point charge of the particle times acceleration. So this particle has both charge and mass. So once it is subject to electric field E, it will experience an acceleration A, given by this formula. And notice that the acceleration is always parallel to electric field E. In this case, electric field points upward, and since the charge is negative, the force points downwards, and since the electric field is uniform, the acceleration will be a constant, therefore having the particle having a parabolic trajectory. So the velocity here, remember for uniformly accelerated motion, this velocity here would be in the y component. So is initial velocity plus acceleration in the y direction times t. It works. Same formula works for both directions. However, this acceleration happens only in the y direction. The corresponding formula for the x direction will have not such term. Remember that in the x direction we will have constant velocity. Now in the y direction we will have this formula. Let me correct this letter here. For the third term is 1/2 acceleration. So let me just correct this formula here for you. And there you go. So same formulas as we used for free fall or parabolic motion, because in this case the acceleration is a constant, just as in the case of parabolic motion. So we can use these formulas for either a particle moving perpendicularly initially in the perpendicular direction to the electric field, or initially in the parallel direction of the electric field. In this picture, the particle is moving initially at 0 velocity and is of course accelerated in the direction of the field. This is a positive charge. So kinetic energy, just as we calculated before, making use of the formulas above, we can readily substitute and find out that the kinetic energy for a particle at a particular instant is 1/2 its charge times the field times the distance between the plates in either one of the pictures. So with this we will end part 1. So as a summary, we've seen the definition of charge, we've seen the definition of Coulomb's law, we have seen the definition of electric field. We calculated the electric field for a point charge and for different charge distributions. And finally, we said that a point charge with mass m and charge q had a motion similar to, well, actually exactly the same as free fall or parabolic motion when the field is uniform. So this is the end of part 1. Would you please go to exercises? I will post a video with examples, and I will see you again in part 2 of the video.